Everyone was aware that a lot of amazing things were about to happen when the James Webb Space Telescope was completely operational, but no one anticipated the recent stunning finding discovered by the telescope. Maybe the entire cosmos is an atom. What is the significance of this finding? And what does it imply for our understanding of the cosmos? Stay tuned to find out more about this startling James Webb Space Telescope revelation that the universe may be made of atoms. You will get to know this and plenty more as we dive into the details of today's show. However, before getting started with the video officially, here's a quick reminder that you can subscribe for free and like the video so that we can boost the algorithm. Comments are most welcomed. Basic grounds. The universe and the small helpless atom have many characteristics. Have you ever thought about how similar our solar system is to a little atom as an example of a part of our cosmos? Although this idea might seem ludicrous, some scientific evidence supports it. In fact, one of the early models of the atom put forth by Niels Bohr in 1913 was influenced by the solar system. According to Bohr, atoms are made up of a nucleus and many electrons that orbit it in a similar way to how planets orbit the sun. The atom solar system model is another name for this model. Let's contrast some of their traits to see how comparable atoms and solar systems are. Similarities. Solar systems and atoms are both incredibly small in relation to the volume of space they occupy. For instance, the diameter of a hydrogen atom is approximately 0.1 nanometers, but the diameter of its nucleus is approximately 0.000001 nanometers. This means that the atom and nucleus are 10,000 times apart, similar to how our solar system's diameter is about 287 billion kilometers, and the sun's diameter is about 1.4 million kilometers. The sun appears to be 200,000 times smaller than our solar system. In both cases, the majority of the space is empty, with only minuscule particles moving. Additionally, there are parallels between electrical and gravitational forces, which serve to hold together the constituent parts of atoms and solar systems respectively. In atoms, these forces are electrical, but in solar systems, they are gravitational. Electrical forces are produced by the charges of particles like protons and electrons, and gravitational poles are produced by the masses of things like planets and stars. However, electrical forces are much larger than gravitational forces, which is why electrons may orbit around nuclei without colliding with them. Both forces are proportional to the distance between the objects, weakening as the distance increases, especially at close ranges. Not just particles, but also electrons and planets can behave like waves, which implies that under certain conditions, they may spread out and cause interference with one another. When electrons pass through a tiny slit, the diffraction pattern they produce on the screen behind it shows that they behave like waves. Similar to gravitational lensing, which bends light waves, gravitational lensing occurs when planets pass close to massive objects like black holes or other stars. In addition to rotating around their centers of gravity, planets and electrons also spin around their own spin angular momentum. A subclass of angular momentum is what attracts this rotation. Unlike orbital angular momentum, spin angular momentum can fluctuate as a result of external forces or interactions with other particles or objects. For instance, by interacting with magnetic fields or other electrons, electrons can flip their spins. Interaction with other planets or tidal forces can also alter a planet's rotation. Solar systems and atoms can both enlarge and contract under particular circumstances. Atoms, for instance, can expand when heated or driven by electric currents or light. In a similar way, solar systems can expand when dark energy or other cosmic forces interact with them. Planets and electrons both follow particular laws or principles that control their orbits and motion. For instance, electrons obey the principles of quantum mechanics, which specify their energy levels and the likelihood that they will be in particular places. Based on their masses and separations from the sun, planets' velocities and trajectories are calculated using classical mechanical principles. There are several proportionalities that link the parts and characteristics of atoms and solar systems. For instance, the radius of an atom depends on its atomic number and the number of protons in its nucleus, whereas the radius of a solar system depends on the mass of its star, which is related to the cube root of the system's mass. Similar to how an electron's energy is inversely proportional to the square of its orbital number, or how many circles a planet makes around its star, so is a planet's orbital period to the square root of its orbital radius. Both solar systems and atoms are components of a larger system that is always growing. For instance, atoms are a part of molecules, which are part of matter, which is a part of the universe, which is expanding as a result of dark energy. Similar to how galaxies are parts of clusters, which are parts of superclusters, which are all expanding as a result of dark energy, so are solar systems. atoms can enlarge or contract as a result of thermal or electrical effects. And in case of the solar system, it is possible for gravitational or cosmic processes to be the cause of expansion or contraction. While solar systems can expand unevenly based on the mix of matter and energy, atoms can expand uniformly in all directions. Another resemblance is apparent when you look across time, while it's important to note that both atoms and solar systems can be linked to a shared genesis. Primordial nucleosynthesis, which took place soon after the Big Bang when protons and neutrons mixed to make the first elements, produced atoms as an example. Similar to how solar systems formed billions of years after the Big Bang, stars and planets were formed from the gravitational collapse of dust and gas clouds. The histories of atoms and solar systems do differ in some ways, though. Atoms, for instance, can alter who they are through nuclear processes like fusion or fission. But solar systems cannot. Through spectroscopy or microscopy, atoms can also be directly studied. But what about the entire universe? Supporting theories. The universe is the totality of all that exists, whereas the atom is the smallest unit of matter with the elemental characteristics, making them appear to be very different in scale and nature. However, several academics and thinkers have drawn attention to the startling parallels between the two. According to one theory, the atom and the universe are both composed of smaller parts that adhere to predetermined patterns and laws. For instance, you are aware that protons, neutrons, and electrons, which make up atoms, interact with one another through electromagnetic and gravity. Similar to how atoms and the structure of the universe can be mathematically and physically explained, galaxies, stars, planets, and other objects interact with one another through forces like gravity and dark energy. This idea contends that both the macrocosm and microcosm may be governed by specific rules or norms. For instance, some physicists have proposed that there might be a theory of everything or unified theory that unifies all natural interactions and events under a single theory. Such a theory would combine general relativity, which describes the behavior of space and time at the largest scales, with quantum physics, which describes the behavior of matter and energy at the lowest scales. Finding such a theory, however, has gone so far to be proven to be challenging and elusive. Nevertheless, there are some contenders such as string theory or loop quantum gravity, even though they have not yet undergone full development or testing. According to a different view of the cosmos and the atom are both expanding through time. Similar to how heated or excited atoms might grow in response to electric currents or light, the universe is expanding as a result of dark energy, an unidentified substance that causes space to stretch more quickly than gravity can bring it back together. The idea that atoms in the universe are both dynamic entities that may change their size and shape raises the possibility that the growth of the microcosm and the macrocosm may have some common causes or effects. For instance, some physicists suggest that the quantum fluctuations of vacuum energy, which are subatomic events, are connected to dark energy. These occurrences result in minute variations in energy and density in a vacuum, which could have a large-scale impact. The cosmological constant problem and the coincidence problem are two examples of defects and paradoxes in this idea, which is yet not fully understood or verified. According to a third theory, the origin of everything is linked to both the universe and the atom. For instance, primordial nucleosynthesis, which took place soon after the Big Bang when protons and neutrons united to create the first elements, produced atoms. Similar to how the universe started, space and time were created when the singularity, an infinitely dense and hot point, erupted. Every atom in the universe has a past that may be linked to a common genesis. According to this theory, the microcosm and macrocosm may have shared characteristics or patterns in their origins. According to a cyclic model of the universe put out by some scientists, for instance, the universe undergoes repeated cycles of expansion and contraction, much like how atoms undergo repeated cycles of excitation and relaxation. A model like this might get around to some of the problems with the traditional Big Bang theory, like the singularity problem and the fine-tuning problem. This paradigm, however, has some difficulties and conflicts, including the entropy problem and the horizon problem, and is not generally accepted or supported by empirical data. The Big Bang and JWST. The Big Bang itself, which is the James Webb Space Telescope has been assisting us in better understanding, suggests that the universe first started as a small, dense point that erupted and expanded quickly. According to the Big Bang theory, the universe was initially very hot and dense, and it quickly expanded to create space-time, matter, and energy. The Big Bang theory is supported by observations and measurements of the cosmic microwave background radiation, the abundance of light elements, the expansion of space, and the formation of galaxies and stars. According to the Big Bang theory, the universe started out as a singularity or point of infinite density and zero volume around 13.8 billion years ago. The Planck epoch, an area of space where the laws of physics were not clearly defined or applicable, encircle the singularity. The singularities in the Planck epoch were extremely hot and energetic, with temperatures exceeding 10 of raised to the power of 32 Kelvin. The next phase of the singularity was known as inflation, and it was a brief period of exponential expansion lasting roughly 10 raised to the power of minus 32 seconds. The universe expanded during inflation by a factor of at least 10 raised to the power of 26, or by orders of magnitude in both temperature and energy. The cosmos became homogeneous and isotropic as a result of inflation, which are both smoothed out any irregularities or fluctuations in the universe's initial state. The seeds for the subsequent structures of the universe were created by the microscopic quantum fluctuations that inflation also produced. The universe went through a process known as reheating after the end of inflation, during which it was surrounded by a hot plasma of elementary particles and radiation. All the particles in the plasma had the same temperature and energy distribution, which indicates that the plasma was in a state of thermal equilibrium. In accordance with the Hubble law, which states that the farther apart the 2 points in space are from one another, the faster they move apart, the plasma was likewise rapidly cooling and expanding. As the cosmos expanded and cooled, it underwent numerous phase transitions or changes in fundamental properties. For instance, the separation of the 4 fundamental forces of nature, gravity, electromagnetism, the strong nuclear force, and the weak nuclear force, took place roughly 10 to the power of 36 seconds after the Big Bang. Quarks, the fundamental units of protons and neutrons, were trapped in hadrons, quark-containing particles, by the strong nuclear force about 10 raised to the power of minus 12 seconds after the Big Bang. Around 10 raised to the power of minus 6 seconds after the Big Bang, electrons, the building blocks of atoms, became electromagnetically bonded to protons, the positively charged hadrons producing neutral atoms, hydrogen and helium. Both atoms and the universe experiencing cooling and condensation, which leads to the emergence of ever more complex structures. The Dark Ages, when the cosmos was fundamentally opaque and dark, had not yet generated any stars or galaxies, came to an end as it expanded and cooled. About 400 million years passed during the Dark Ages before the first stars and galaxies emerged as a result of the gravitational collapse of gas clouds. These galaxies and stars produced light and radiation that ionized and the surrounding gas, making the universe transparent and observable once more. This marks the beginning of the cosmic dawn and is referred to as the re-ionization phase. The early stars and galaxies were very different from those we see now. They were considerably bigger, hotter, and brighter, and they had much shorter lives. Heavy elements like carbon, oxygen, nitrogen, and iron are also generated through nuclear fusion and supernova explosions. These heavy substances improved the interstellar medium, promoting the formation of more diverse forms of stars and planets. Furthermore, early galaxies were smaller, more erratic, and more clustered than they are now. Additionally, they combined and interacted more often, eventually leading to larger and more intricate structures. The universe has been expanding and changing ever since the Big Bang. Some of the phases and transitions that the universe has seen include inflation, reheating, nucleosynthesis, recombination, the Dark Ages, reionization, star formation, galaxy formation, structure formation, and the dominance of dark energy. Dark energy, a mysterious force that speeds up the expansion of space, dominates the phase of the cosmos that is currently in existence. The universe's future depends on the characteristics and behavior of dark energy. The Big Bounce, in which the cosmos expands, the Big Freeze, in which the universe becomes cold and empty, the Big Rip, in which the universe splits apart, the Big Crunch, in which the universe collapses into a singularity. Cycles of expansion and contraction are all conceivable scenarios. Investigating the early universe from the Big Bang to around 1 billion years later is one of the JWST's main objectives. The JWST uses its infrared vision to peek back over 13.5 billion years in time to observe the first stars and galaxies emerge from the early universe's darkness. JWST can observe far-off objects that have been redshifted due to space expansion using infrared light, despite the fact that it is invisible to human sight and can travel through dust and gas that block visible light. The JWST has already made some remarkable discoveries in its first year of observations. It has found some of the oldest and most distant galaxies ever found, some of which date back to just 1 billion years after the Big Bang. These galaxies are so massive and brilliant, though, that they challenge some of the theories about how galaxies form and evolve. The JWST has also looked into some of the earliest molecules in the universe that eventually became atoms, which are the fundamental building blocks of matter and life. Indicators of the physical conditions and chemical processes that existed in the early cosmos include temperature, density, pressure, ionization, radiation, and reactions. They also shed light on the production and distribution of mass and energy in the early universe. Several of the universe's earliest supernova explosions, which are potent events that happen when massive stars die, have also been discovered by the JWST. These supernova are important sources of cosmic rays and heavy metals, which have an effect on the environment's chemical makeup and energy balance. They also provide information on the characteristics and evolution of their progenitor stars. The early quasars and black holes of the cosmos, which are extremely brilliant and massive objects that produce enormous jets of radiation and matter, are also being studied by the JWST. Due to their ability to reveal details on the birth and evolution of galaxies, the distribution and makeup of dark matter, and the effects of gravity and relativity, these quasars and black holes are important early universe probes. What do you think of this comparison? Do let us know your thoughts in the comments section below. If you enjoyed this video, please hit that thumbs up. It will help us to understand our audience and allows YouTube to suggest similar videos to you. Thanks for watching, and we hope to see you at the next one.